we're now start dealing with rotational motion. No, I think I do need the whole thing first. Okay. All right, what do I mean by doubling the number of equations is we start out with a bunch of linear equations and quantities. We've talked about momentum, we talked about position, velocity, things like that. Well, we're now going to get into things rotating. So second about the velocity of this is a little bit difficult to sum up easily because the velocity is different in different spots. So we need to start talking about how do we describe things turning. Not scalar. Linear/translational motion. I think I generally call it linear motion, but if you ever see the word translational, it means the same thing. So we have something known as position. S, X, various things. But there is an analog, a rotational analog. So over here, rotational/angular. Now, I write a rotational and angular, they are interchangeable. Later on, we'll talk about angular velocity, but if you said rotational velocity, people know what you're saying. Physicists are not going to look down at you for saying rotational velocity. But tradition is to generally call it angular. All right, so what do you suppose is the rotational analog of position?
Like the symbol for it?
Or the name?
The name, rotational analog for position.
It is not angular position, by the way. All right, I am going to spoil this one for you. At some point, you will catch the pattern. This is called angle.
Oh.
The symbol for angle is, the ones that I use the most are theta and phi, theta and phi. I've seen a lot of things being used for angle. Probably the one that really messed me up, pi should never be used for an angle. I have seen that in one textbook. Got really confused about how pi showed up in an equation. And it took me a while before I figured out, oh, it's a variable. Yeah, never use pi for a variable. I don't know what the person was thinking. All right. We have velocity, symbolized by a V with the vector symbol. The rotational or angular equivalent. What's the rotational or angular analog of velocity? And I mentioned it about 5 minutes ago.
Cosine? No.
What?
Cosine?
No.
No.
Angular velocity. That's a theta. That's a phi. The symbol for angular velocity is an omega. It's a lowercase omega. It looks kind of like a W. It's not a W. You'll notice we're dealing with Greek letters over here. Doesn't always, it's not always Greek letters, but Greek letters seem to show up a lot when you're dealing with rotation. have acceleration. What do you suppose is the rotational or angular analog to acceleration?
Angular
Ang-
acceleration.
Somebody just said it.
Angular acceleration.
Yes, that's it. You want to take a shot at what the symbol is? Anyone?
Like a beta?
Now we're using theta up there.
Beta with a
Oh,
B?
beta. No, generally, if in doubt, think acceleration starts with an A. What Greek letter starts with an A?
Alpha.
That's
Alpha.
the one, alpha. All right, so those are the basic, time. What do you suppose the rotational angular analog of time is?
Angular time,
No, it's just time.
It's just time, okay.
Yeah, time stays the same. I've often thought about angular time and wondering what exactly that would be. But the time it takes for something to go around is the same time it would take for something to go straight. I mean, there's no difference in that. Force. I will spoil it. It is torque. The symbol is a cow. The next thing is, I would consider my most obscure reference. Except I've had two people who've known what the reference was, which is shocking. I will sometimes refer to torque, as Jitu Kumbuka. I will not explain the reference yet. But if you refer to it as Jitu Kumbuka, the only people who probably will understand the reference would be me, students I've had previously, or the grandfather of one student or the father of another student. The two students who got the reference did not know firsthand what the reference was, but remembered it from what the dad and the grandfather had told them. Mass. I don't really care for the terms here, but I'm sort of stuck with it. The rotational analog of mass. So mass, if you think of mass as how hard it is to get something to change its velocity. The greater the mass, so if I apply a force to a mass, the greater the mass, the lower the acceleration. So the rotational analog of it is if I need something to rotate, the harder it is to rotate, the greater this quantity is, or to give it angular acceleration. And it goes by two names. It's either called rotational inertia, or the term that I tend to use is moment of inertia. Just depends upon which textbook you happen to be using. The symbol for it, we finally get away from the Greek letters, is just a capital I. So great, you got a bunch of new letters. How does this double the number of equations? This is how. We'll take Newton's second law of motion, F equals ma. To get the rotational analog of it, you just transliterate. Instead of force, well, force relates to torque. Instead of mass, we have moment of inertia. Instead of acceleration, we have angular acceleration. the total torque acting on an object is equal to the moment of inertia times the angular acceleration. Just like this, the total force is equal to mass times the acceleration. I will get into more detail about what torque is and what I is, just setting up some basics. I'm going to take an equation that we didn't, it's in one of the videos, I know that. So delta x equals VIT, that's an I, plus 1/2 AT squared. We've dealt with that part of the equation and dealt with that part of the equation, but they actually combine. What would be the rotational analog of this equation?
Omega
For what?
for, oh, sorry, velocity. Oh, I should have started with theta, sorry. Okay, theta equals omega. Change in theta equals omega times time. That's the same, plus 1/2 times alpha time squared.
Okay. Now something that we'll hit on more directly. I have kinetic energy is 1/2 mv squared. What would rotational kinetic energy be?
One half times I times omega squared.
Now this seems somewhat contradictory for those who remember why I wanted you to memorize 1/2 mv squared. If you forgot, I wanted you to know what 1/2, the kinetic energy is 1/2 mv squared, because I said that formula doesn't change. You're working on your Nobel Prize winning work, it's still 1/2 mv squared. But now I'm saying there's another formula? Well, it comes down to, if I want to figure out the speed of an object, if we think about, there's a piece of tape here, and then I've got tape here attached to the yellow Post-it note. Think about how much time it takes for them to go around once. Which goes around once faster? This tape or this tape? Sorry, misworded. Which one takes more time to go all the way around a circle once?
The one
No.
that's that.
Neither.
And fight.
I agree with her.
Pardon? You agree with her?
Yeah.
Are they both going the same speed
Let's be careful about the wording there.
or same?
Is it the
velocity?
same? So let's start with time. Is it the same time?
Yeah.
Yeah. This is known as a rigid object. For a rigid object, the time would be the same. It takes the same amount of time for them both to go around. Now, which one travels a greater distance?
On the outside.
Yes. That one's traveling that big circle, and this one's traveling a smaller circle.
Oh, okay.
So this one travels a greater distance in the same amount of time as this does. So this one is traveling at a faster speed. However, they both go around the same angle in the same amount of time. They have the same angular speed. They have different speeds, but the same angular speed. And so because of an object that's rotating, things are traveling at different speeds, linear speeds. We have to somehow deal with that, and so the 1/2 mv squared it's in there. Like spaghetti sauce, it's in there. Is it ragu? Who had the ad campaign? It's in there.
I don't remember that one. We're useless.
Next thing you know, you're gonna say that was an ad campaign from before you were born. All right, questions up to here?
It's Prego.
I was about to.
Prego.
Yeah.
Yay, internet. All right, so I have this thing going around and I need to describe the angular motion. So we'll start out with angular velocity. It'd be, well, how the angle it passes through or goes through divided by time. But angular velocity is a vector. Got the vector symbol right there. That means there's a direction. So what is the direction? How would you describe the direction of that spin?
To your left.
To my left.
Stay to the left.
Or clockwise.
That's going to my left, that's going to my right.
That's true.
It's going clockwise.
It's counterclockwise to me. So we could go through and say, well, when it's spinning at the front of the room and you're in the back of the room, then to you it looks clockwise. That's a whole lot of words. We want to come up with some way of doing this that we don't have to describe where you're standing when you do this. Because we run into that issue of it's clockwise to you, counterclockwise to me, vice versa. So the powers that be came up with a decision, and they will employ the right-hand rule. Who are the left-handed people in here? No left-handed people? Okay. That makes that part easier. Then I go into the bid. It's not the dominant hand rule, it's the right-hand rule. So what you're gonna do, I have an axle right here that's going basically front to back. So my right-hand rule, my thumb is gonna point in the direction of the axle. So that's either I'm pointing towards the front of the board, or front of the room, or to the back of the room. My fingers, I want my fingers to curl in the direction this is turning. So if it's spinning like that, well, if I point my thumb to the back of the room, my fingers are curled opposite the direction that it's spinning. So I want to point my fingers toward the front of the room, my fingers curl in the direction of the spin, so the angular velocity is to the front of the room. This is what they decided. If I spin it like this, the angular velocity, again, my axle is now vertical, so my thumb's either going to point down or point up. I want my fingers to curl in the direction of the spin, which is like that. My thumb's pointing down, so the angular velocity is down. Let's check it out. If I close that door, what would be the direction of the angular velocity of the door as it closes? Right hand. Think about the axle, or the axis of rotation. Your thumb's going to point along that line.
You mean of the door moving?
Yeah.
So it'd be like your hand on the handle?
What's the axis
would
of
you-
rotation? What is the axle? What is it rotating about?
Your hinges.
The hinge.
The hinges. So the
Yeah.
hinges are running vertically.
Mhm.
So my thumb's either pointing up or pointing down. If the door is closing,
Should be up, so it's up.
yes. As that door closes, the angular velocity will be up.
Because the hinges are vertical?
Yeah. If I open the door, the angular velocity would be down. Because the door, if I'm opening it, the door's rotating that way.
Okay.
If I'm closing it, it's rotating that way. I did not make this stuff up. Now, I will say that when I was first taking physics and they were talking about angular velocity being up or down on the door, it really confused me because I kept thinking, what's going up? I see the door spinning this way, but what's up? Because I had trouble making the leap of, there's nothing going up. Nothing physically is going upwards. This is just the convention. This is just what they decided, and it works out nice mathematically, that how to decide the direction of these things that are spinning. So if I said I had a door and it is going to, the angular velocity is up when I close it, it doesn't matter where I'm standing, I know that it's going to have to swing that way in order to close. If I said the angular velocity is to the back of the room, or is pointing that way, well, if the angular velocity is that way, that means it has to be spinning like that, which would be clockwise for me, counterclockwise for you.
Is there another example of another object?
Is this thing? Oh, that's not what I want. It was really convenient when I was in a room with a door that opened in towards the room.
Okay.
But in absence of that. We'll make our own door. What is the direction of the angular velocity? I heard up. Is that your left hand?
Yeah.
Right hand.
This way is up. Right?
That-
This way?
So, where's the axis of rotation?
On the
No.
hinge or the crease.
Okay, right there. So my thumb, it is vertical, so my thumb's up or down. If my thumb is up, that means that this is gonna be rotating like that. That's up. That is the angular velocity. is
So your
down.
hand is the door.
Yes,
Okay.
My hand is the door.
I'm sorry.
I don't know. This makes no sense.
years ago, there's a lot of right-hand rules when you get to electricity and magnetism. And I was given a test where there's a whole lot of use of right-hand rule. And a regret is that I didn't film it. Because for the first 20 minutes of the test, there were a lot of people doing this. And I would have liked to have filmed it and then set it to music. It's like hand ballet. Questions up to here?
So if you're holding it like this, it is coming towards you, it's up.
I hesitate to. All right, so if it's up, if I'm standing over here, it's coming towards me and it is up. If I'm standing here, if it's coming towards me, that one's down. Because the rotation is like that. So if my thumb